Vamos a empezar. Buenos días a todos. Yo soy Sol Carretero Palacios, soy científica titular en el Instituto de Ciencia de Materiales de Madrid, de CSIC también. Vamos a proceder a la defensa de tesis de Juan Ramón Deop para el título de doctor por la Universidad Autónoma de Madrid. Os explico brevemente el procedimiento. Voy a presentar al tribunal primero, después seguiremos con la presentación del candidato, que tienes entre 45 y 60 minutos para hacer tu presentación. Se recuerda que no deberíamos aplaudir después de su presentación. Después seguimos con un turno de preguntas con el tribunal, que iré dirigiendo yo. Seguiremos con la pregunta clave de si hay algún doctor en la sala que quiera hacer una pregunta. Después, los asistentes debéis salir fuera. El comité deliberaremos dentro la calificación final. Volveremos a invitaros a entrar. Se dará la calificación. En este caso, si hubiera sobresaliente, no se dice el cum laude porque es un voto secreto. Esto lo conocerás dentro de unos días, supongo, por la Universidad Autónoma de Madrid. Y creo que esto es todo. Tenéis los estudiantes de doctorado la posibilidad de firmar al final de todo un papel para que os cuente para vuestro programa de doctorado individual, ¿vale? La presentación ha sido en español, ya la habéis visto, pero a partir de este momento voy a hacer la presentación de tribunal y luego cambiamos al inglés. Entonces tenemos a Francesco Intravalla, que viene como profesor titular de la Universidad de Humboldt de Berlín. Después tenemos a Manuel Marqués, que es profesor titular en la Universidad Autónoma de Madrid. Ramón Paniagua, que viene del Instituto de CSIC, pero no sé cuál. Estructura de la materia. Y perdóname, Ángela, porque no me sé tu apellido. ¿Cómo? Barreda, que es investigadora Ramón y Cajal de la Universidad Carlos III. So now we change to English. So whenever you want, you can start. I give you this in case you need it.
Okay, so welcome to my presentation, where I'm going to present the work that I did during my PhD thesis in the Consejo Superior de Investigaciones Científicas, CSIC, between the Instituto de Óptica and the Instituto de Química Física, where we are located now. And, well, my thesis is in the context of the programa de doctorado en Física de la Materia Condensada, Nanociencia y Biofísica, and it has been supervised by my thesis advisor, Alejandro Manjabacas. And the title of my talk is Collective Resonances and Fluctuating Electromagnetic Fields in Nanophotonics. So let's start by talking a bit about nanophotonics. So nanophotonics is the study of light interacting with the structures with features in the nanometer scale. And we are especially interested in this topic because when the feature sizes of the objects approach the wavelength of light, new optical phenomena, new physical phenomena emerge. This is a field that has grown a lot in recent years, and there are several different research directions, but I have focused in my thesis in two main research directions that I'm going to introduce. The first of them is lattice resonances in periodic arrays of metallic nanostructures. And the way I have contributed to this research direction is by exploring new materials that support these lattice resonances, in particular graphene, also exploring new geometries, changing the unit cell by adding more nanostructures, more than one nanostructure per unit cell, giving rise to new physical effects. And I have also explored the role of the excitation source to excite these resonances and trying to bridge a gap between previous theoretical results and experiments. In a different direction, I have also explored phenomena induced by fluctuating electromagnetic fields, a field that is really interesting because these kind of electromagnetic fields can mediate the transfer of momentum and energy between nanostructures, and in this context I have explored the propulsion of nanostructures by means of thermal radiation I have also explored the effects that arise because of the relative motion of the object and the thermal radiation. And I have also studied the interplay between the energy and momentum transfer and how each other are modified. So let's start by the lattice resonances in periodic arrays of metallic nanostructures. As I said, these modes appear when our array of nanostructure is periodic. We need a periodic arrangement that enables the multiple coherent scattering between the elements of the array, giving rise to a coherent interaction. And these lattice resonances have really nice properties, strong responses, and also narrow optical responses, especially compared with the individual constituents, the individual nanostructures conforming the array. Now, let's see some examples of what these periodic arrays can be beneficial for. We can use them for light emission and lasing. For example, using these narrow resonances as feedback for a lasing system. We can also use the field enhancement provided by these resonances for some sensing applications, for example, in surface enhanced Raman spectroscopy. We can also use them for building reconfigurable metal lenses. Or we can use the property of metallic nanostructures that can turn light into heat to explore the field of thermoplasmonics. And thanks to the flexibility of engineering an arbitrary unit cell, we can get some complex interactions, for example, chiral light matter interactions. So let's understand the properties of the modes and why they are so interesting. It is many times useful to understand the properties of a periodic array in terms of its constituents, the individual nanostructures. And we know that when we have such a nanostructure whose dimensions are much smaller than the wavelength of light, or small enough, we can model these structures in the dipole approximation, in which the optical response is included in the particle polarizability. These individual nanostructures also support resonances, that in the case of metallic nanostructures are usually particle plasmons. Now, if we move to a periodic array, in which the wavelength roughly matches the periodicity of the array, we now have to modify this expression here, because we have to take into account the interactions, giving rise to this slightly different expression where we have the response of the individual nanostructures, but also their interactions through this term that we call the lattice sum. This lattice sum, we can understand it as a sum, and an infinite sum in principle in a periodic array over the scattered waves by each element that is spread through this sum, where I keep here only the far field component of the scattered wave, which is going to give us very interesting effects, especially when these terms are in phase, because then all of the terms will add up constructively. This occurs only for certain wavelengths that are commensurate with the periodicity of the array. And in such cases, we have these kind of divergences that we know as Rayleigh anomalies, where the lattice sum attains arbitrarily large values. Now, in the same way that we can understand the plasmons as the poles of the polarizability of the individual nanostructures, now, when these two functions intersect, we are going to have a pole of this kind of effective polarizability of the array. And when this happens, a new resonance will arise, a lattice resonance, that is now a mode of the whole system, of the whole periodic array, because it encompasses both the response of the individual nanostructures and their interactions. And note that it can achieve a much narrower spectral profile, thanks to the fact that this lattice sum is really dispersive. So this intersection between these two functions occurs only in a really narrow spectral region. So in this first section of this topic of lattice resonances, I'm going to explore the possibility of new materials that support these lattice resonances, unlike the mostly explored dielectric or noble metal nanostructures. And in particular, we are going to explore graphene, which is a two-dimensional material formed by a honeycomb of lattice of carbon atoms, with really nice electronic and optical properties that arise from its band structure. We see that we have a completely filled valence band, an empty conduction band, and we have a zero band gap. So in principle, we don't have electrons in the conduction band, and it couldn't, for example, sustain localized surface plasmons. But if we dope it, if we add electrons to the conduction band, then graphene becomes conductive, and it can sustain localized surface plasmon. So let's see how we can do that. Well-known method is the so-called electrostatic gating, in which we connect, we apply a potential to graphene in a sort of capacitor configuration, and in this way, our graphene layer will get charged, and the conduction band will get filled up to a certain Fermi energy. And by playing with this Fermi energy, we can obtain plasmons that are tunable, that have different properties. We see here a blue shift as we increase the Fermi energy. Now, something interesting here is that, well, this is expressed in photon energy, but if you express it in wavelength, you can see that the resonance wavelength is approximately on the order of 10 microns, while the size of this nanostructure is of the order of 15 nanometers. And this is not going to help us to achieve lattice resonances. Because in order to achieve a lattice resonance, as I was indicating before, we need a wavelength that matches the periodicity of the array. So if we try to achieve a lattice resonance with this size of nanodisk, we're going to obtain this kind of array, in which the graphene nanostructures occupy a really small portion of the array. We have a really small filling fraction. And indeed, to observe that this is indeed a graphene nanodisk, I have to zoom in, right? So let's see how can we solve this problem. We are going to take advantage of the fact of this mismatch between size and wavelength to model graphene in a quasi-static approximation, in which its response can be described by an electrostatic potential, as it will be done in electrostatics. And in this way, we can obtain this really general polarizability that depends on some parameters that only depend on the geometry of the nanostructure, but not on the actual size. And then we introduce the material properties through the conductivity through the model. Now, with this polarizability, we can now derive the ratio between the diameter, the size of the nanostructure, and the resonance wavelength. And we can see that this increases with diameter and Fermi energy. So what we have to do is working with high diameter and Fermi energy. For example, we are going to use a Fermi energy of 1 electron volt and a diameter of 10 microns. Let's explore a case. I'm going to analyze the optical response of the nanostructures by means of the extinction cross-section that more or less tell us how much light is removed from the incident excitation. And we plot it for this polarizability, obtaining this result. We can see a resonance, a particle plasmon. But now, if we compare the results that we obtain for this quasi-static polarizability with finite element method simulations, we see that there is a big mismatch. And this is something that actually we could expect, because by choosing these parameters, by going to high diameters and Fermi energies, now we have a diameter that is smaller, but at least comparable to the resonance wavelength, and we are moving beyond the regime of application of the quasi-static approximation. So to improve our model, we have to introduce some electrodynamic corrections that we can see here. We can see that now there is a much better result, and we can even derive analytically the redshift of the resonance that we see from the quasi-static model to these electrodynamic corrections. Let's move to the actual array. What we are looking is for lattice resonance in a periodic array of graphene nanostructures. So let's generalize our extinction cross-section by the definition of the extinction efficiency, in which now the polarizability has been substituted from the polarizability of the nanostructure to the polarizability, effective polarizability of the array, including, as we saw before, the individual polarizability and the lattice sum, the interaction. Let's analyze some results for a period that is twice the size of the nanostructure for different levels of doping, different Fermi energies, and what we see is some broad resonances that actually resemble a lot the localized plasmons. Indeed, if we plot with dotted lines the resonance wavelength of these plasmons, we see that they coincide almost perfectly with these resonances. And note that this occurs for a period that is smaller than the resonant wavelength of the plasmon. However, if we move to the opposite limit, in which we now have a much larger period that is 7 times that of the size of the diameter, we plot for the lower level of doping, we see some similar results, but as we increase the level of doping, the resonance wavelength is going to cross the value of the wavelength that matches the period. It's going to cross the Rayleigh anomaly, and in this case, a new resonance with extremely narrow profile, so narrow that here it just looks like a line in this scale, arises. And this happens for a period that is larger than the wavelength. So this indicates our condition for sustaining a lattice resonance. We need a period that is larger than the resonance wavelength of the individual nanostructure. I also analyzed some individual cases, some intermediate cases, sorry, where we can see this transition to a more collective mode, and also some results for a different diameter, where we again have a regime in which we support some resonances that look like localized surface plasmons, maybe a bit modified by first neighbors interactions, and we move to a regime in which we have lattice resonance, and even in this case we have some second order lattice resonances. We compare our really simple model that just composed, just models each particle as an electric dipole with finite element method, full wave solutions of Maxwell equations, with really nice results in both regimes. You can see that there is a really good match. And by comparing the left and right panels, we can realize something really interesting. We can see that the peak extinction efficiency in left and right is the same. So it looks like it doesn't depend on the diameters independently, but only on the ratio of period to the diameter. So to analyze this in more detail, I calculated analytically the peak extinction efficiency. I did so by applying the definition of the extinction efficiency, the definition of the polarizability array, applying all the analytical expressions that we already know, and imposing a resonance condition in which, as we saw before, the inverse of the polarizability is crossing the lattice sum. With all of these ingredients, we can obtain an analytical expression for the peak extinction efficiency that, as we see here, only depends on the ratio of the period to the diameter, as we suspected. If we compare it to some numerical results that I showed to you before for 10 microns and 20 microns diameter, and compare it with this function, this expression, analytical expression that I plot with this solid curve, we can see that there is a really good match. And the same for the rest of the cases that I analyzed. Now, we can also derive analytical expressions for the rest of the quantities characterizing our resonance. It's going to be a bit faster here, the resonance wavelength and the quality factor. And to do so, we can separate into two regimes. First, the regime in which we don't support lattice resonances, so the response is dominated by the individual nanostructures. In this case, the inverse of the polarizability crosses the lattice sum in a region where the lattice sum is not large enough, and the opposite regime in which we have really large values of the lattice sum. This allows us to derive some closed form analytical expressions, and I'm going to show you here how they compare to the numerical results. In one regime, we plot it with this dash curve. We see that there is a really good match, and also a really good match in the opposite regime. And only in this transition region, it can maybe deviate a bit more. The same for the quality factor, excellent match in both regimes, and we can see how the quality factor, once we are able to sustain a lattice resonance, grows by several orders of magnitude as we increase the period. We also obtain really good match with the rest of the numerical results that I explored. Now, I have shown you the possibility of exciting lattice resonances in periodic arrays of graphene disks, but we've seen that it has some steep dependence on the period. The filling fraction decreases with the period squared, and for this reason, maybe it will be interesting to explore an alternative configuration, like this array of graphene ribbons, in which the filling fraction decreases with the period. However, there are more differences. Here we have a localized plasmon that is degenerate in x and y directions, where the lattice sum and the interaction is also degenerate in both directions, such that if we have, we know that because lattice resonance is coupled through far field direction, this is orthogonal to the polarization. And no matter what polarization we choose, we always have an orthogonal direction in which the array is periodic. However, this is not the case in the array of graphene ribbons. In this case, we have that the plasmon of the ribbons is fully polarized in the x direction. However, the array is not periodic in the orthogonal direction, and this is going to give us problem. Let me show to you. If we plot the polarizability of the ribbon in the x direction, we can see a nice particle plasmon. However, the lattice sum in this direction doesn't diverge, and thus it doesn't attain large values. On the other hand, the orthogonal direction, the y direction, since the ribbon is ideally infinitely extended in this direction, it doesn't become resonant, and we can only see some dispersion associated with the conductivity of graphene. However, in this direction, the lattice is actually resonant, and it diverges. So we have a problem, because we have ribbons that are resonant in one direction and a lattice that is resonant in the other direction. So how can we solve that? Well, what I thought is that it would be nice to apply a magnetic field that is able to mix X and Y polarizations, and in this way, maybe we can sustain a lattice resonance. Let's check it. We again study the response through the extinction efficiency of our array, and I plot here the results in the absence of a magnetic field. We can see something that looks like a particle plasmon, a broad resonance, and as we turn on the magnetic field, we can observe the emergence of a new resonance with a really narrow profile, a lattice resonance. So this method actually works. And we can see that if we plot the quality factor against the magnetic field, we see that once we are able to sustain a lattice resonance around 7 Tesla, the quality factor increases by several orders of magnitude. And the same for some other cases that I studied. So we have seen that we can use graphene as an alternative material to sustain lattice resonances. Now I'm going to focus a bit more on the geometry of the array. And in particular, we are going to use the interactions in an array with a complex unit cell with 2 nanostructures per unit cell to solve a problem, which is the fact that if we want to excite a resonance whose dipoles lie out of plane, are perpendicular to the plane of the array, then it's going to be really difficult if we can come with a field that is polarized in the plane of the array. Let's just understand first why these resonances are so relevant. So far we have seen in-plane modes that if we plot this from a side view, we can see that its radiation pattern, this configuration favors the radiation of energy out of the array. However, if we have now our dipoles perpendicular to the plane of the array, we have a configuration in which these radiative losses are inhibited. They are highly suppressed, giving rise to large quality factors and also large field enhancements. However, we have a problem here, because if this array cannot couple to far-field radiation, if it cannot radiate energy, it also means that it's going to be really difficult for us to come with far-field radiation and excite this mode. Let's see how bipartite arrays can help us. Let's start with a monopartite array, like the ones that we have studied before. And in this case, we have seen that we can analyze the dipoles by solving this equation, including the response of the nanostructures and their interaction. And we have to solve it self-consistently to obtain the dipole. Okay? Now, in a bipartite array, we now have our initial monopartite array, but we are going to add a second monopartite array. And the interaction, of course, is going to depend in their relative position between these two particles. And now, because we have two sort of monopartite arrays, now we have to include the coupling between these two arrays, two individual arrays, by means of these Gij factors. Now, what I'm going to explore is a bit more different, because not only we have a bipartite array, but each nanostructure is modeled as an electric dipole and a magnetic dipole. And now we are going to consider the coupling between these electric and magnetic dipoles through these GEM terms, these electric magnetic interaction terms, because we are going to come with an electromagnetic field exciting both electric dipoles and magnetic dipoles. And these coupling terms, these electric magnetic coupling terms, are going to be really interesting because they are all able to couple in-plane and out-of-plane components. And this is exactly what we want to come with an in-plane polarized electric field and excite an out-of-plane resonance. The working principle is going to be the following. We are going to come with our electromagnetic field. We are going to excite in-plane magnetic dipoles, and thanks to this interaction, these magnetic dipoles will excite an out-of-plane dipole. Let's check if this works. I'm going to plot the optical response, the absorbance, and the reflectance of our array. Now we have two distinct resonances, so to ascertain their nature, I'm going to plot the out-of-plane electric dipole. We observe that the out-of-plane electric dipole of both nanostructures attains large values in the exact region of this resonance that has a large absorbance, a small reflectance, and a narrower profile, the properties of an out-of-plane resonance. And something interesting, so this is actually an out-of-plane lattice resonance. And something interesting is that we can observe that the two nanostructures are in antiphase. The two out-of-plane dipoles are in opposite directions. Now for completitude, I'm also going to show that the other resonance is a more conventional in-plane resonance. And I also show you here the results of finite element method simulation, showing that there is a really good match with our model. That again is really simple. Every nanostructure is just an electric and a magnetic dipole, but still we obtain a really good match with full wave simulations. We can also use these full wave simulations for studying the surface charge density, and see that the oscillation of the surface charge density corresponds with an out-of-plane oscillation, and we can also see here the opposite orientation of the two dipoles. I also use these finite element method simulations to study the electric field enhancement and also the magnetic field enhancement, and we can see that the fields are actually greatly enhanced around the whole unit cell. And because of this opposite orientation of the dipoles, we can see that in the case of the electric field, this is minimized, but in the magnetic field, it is maximized, and it actually attains really large values. We also observe that even if we move far away from the plane of the array, 2 periods, for example, we still observe a great enhancement. Now, I have shown to you how we can obtain lattice resonances with new materials and new effects arising from the geometry. But something really interesting and crucial, I will say, that maybe was missing in literature is analysis of the role of the excitation source, of how we excite these resonances. Because most studies just focus on plane wave illumination. And this is just an approximation. It's not something that we can actually produce. So what is the actual role of an excitation source that has a finite size? And when do we approach this plane wave limit? So to analyze this, I model my electric field by means of this Fourier transform, which you can understand just as a sum over plane waves with a certain amplitude. And I define this beam, which is mainly polarized in the x direction and has a Gaussian envelope. And very importantly, we are going to control the size of this beam in real space by means of this W0 parameter that you can understand as the beam width. Let's analyze a case for a period of 300 nanometer. It's a small period. And here you see the results for a beam width that is just equal to 1 period. So we are roughly illuminating just one particle. We see that even though we are just illuminating one particle, we see a strong response. And in fact, just by going to a beam width that is 4 periods, we converge to the plane wave limit. However, if we move to a regime in which we have highly collective resonances with a higher period, we see that for a small beam width, we obtain almost no response. And we have to increase the beam width a lot, up to 800 periods, to obtain our full lattice resonance. Note that here, although these look like these resonances have the same width, we have here a really different scale. This is a much narrower resonance with a much larger quality factor. Because it's a more collective resonance, we need to eliminate more and more particles to sustain this resonance. This is why, in this case, this resonance is not highly collective, maybe just first neighbors interactions, and we convert to the results really fast, while here, this is not that simple. We can analyze this in more detail by plotting the extinction efficiency, normalize the peak extinction efficiency, normalize to the plane wave limit, and we see that for increasingly collective arrays with higher period, we need a larger and larger beam width. The same happens for the quality factor. We see that as we increase the period, the quality factor of the resonance increases, but to see actually this quality factor, we need increasingly large beam widths. This characterizes the far field properties of our modes, but it is also really interesting to analyze the local excitation of the dipoles. And we can see that there are huge variations as well, depending on the beam width. We can see that if we come with a beam width with a beam that is really focused, we can actually observe how the excitation propagates. And since we are coming with expolarization, this is propagating in the interaction is propagating in the y direction. As we increase the size of the beam, then we converge to a limit in which the excitations of the dipole follow more or less the profile of the beam. This is something that we can also observe by making cuts, but I'm not going to focus this too much. And we also explore this in by a reciprocal space study. This finishes this part of my talk, centered on lattice resonances in periodic arrays of metallic nanostructures. Now we will shift gears a bit to phenomena induced by fluctuating electromagnetic fields, focusing on two concepts: thermal radiation or radiative heat transfer, and Casimir interactions, both arising from these fluctuating electromagnetic fields, and how these two concepts can appear at the same time and give rise to interesting results. We're going to start by saying something that we already know, that material objects transfer energy by emitting and absorbing electromagnetic radiation. And this is something that is especially evident in the case of an incandescent metal, but common for every object at a finite temperature. And in particular, because we are at around 300 Kelvin, we also emit in the infrared. All of this can be explained with Planck's law of black body radiation. That includes a temperature dependence through the Bose-Einstein distribution. And in this way, it can explain the fine displacement of thermal radiation towards shorter wavelengths as we increase temperature. Now, nowadays, radiative heat transfer is still pretty much under research because of its many applications, many of which are related to waste heat recovery, which is the concept behind the field of thermophotovoltaics, in which we would like to heat up this emitter that will in this way emit thermal radiation that could be absorbed by a power cell, by a photovoltaic cell, and turn this thermal radiation into electrical power. There are some other applications related with heat management, and also some more exotic idea like this thermal camouflage idea with multi-layer graphene. Now let's see how can we understand radiative heat transfer in terms of the fluctuations. Well, we know that the electromagnetic field fluctuates due to temperature and because of its quantum nature. And we have a nanostructure with a fluctuating current. We can understand it classically as an oscillation of charges, and we know that when such a thing happens, we will have it will emit electromagnetic energy, thermal radiation, and of course these fluctuations will be controlled by the Bose-Einstein distribution. Now, while in the macro scale or for extended systems, this gives rise to black body radiation, this is going to be a bit modified in the nanoscale because we now have this ratio of the absorption cross-section to the physical area, the geometrical area of the nanostructure. And while for extended structures, this ratio will be less than 1, giving rise to gray bodies or black bodies in the best case. For nanostructures, we can have absorption cross-sections that are larger than the geometrical area. And in such a way, we can have nanostructures that will emit or absorb more than what they were supposed to do according to the geometrical area. Not only that, but in the nanoscale, if objects are in close proximity, we can also make use of the evanescent fields to further increase this transfer of energy. Okay, another field that it's related to the fluctuations of the electromagnetic field is Casimir interactions. And to explain Casimir interactions, I'm going to focus in an example in van der Waals forces that we can understand in the same way. We have a structure with a fluctuating dipole, and this fluctuating dipole will induce an electromagnetic field in the surrounding structures that will at the same time induce a dipole that will interact with our first dipole, giving rise to an attractive force that is the van der Waals force, including the response of both nanostructures and also their separation. And there is actually a whole family of these forces arising from the fluctuations of the electromagnetic field, which is what we know as Casimir interaction. Let's see some more examples. There is also an attractive force known as the Casimir force between two conductive plates that it's many times explained because of the different density of photonic states outside and inside these two conductive plates. If we break some symmetries of the system, for example, by considering anisotropic objects, we can also obtain a Casimir torque. And while these phenomena are really interesting by themselves, they can also have applications. And recently, they have been utilized to build self-assembled cavities that, depending on their properties of the nanostructures and the surrounding medium, can have different optical resonances that we see here as different colors. And they could even study in real time the Casimir self-alignment of this system, of this nanocavity, in a time scale of seconds. So we have seen two different kinds of fluctuation-induced phenomena, radiative heat transfer and Casimir interactions, that even if they look really different, they arise from similar physical principles. And what I thought that it would be really interesting is to study systems in which these two concepts play a relevant role, and maybe study their interplay. In this context, the first work that I'm going to show to you is the possibility of propelling a nanostructure by means of thermal radiation. We know that light carries momentum and it can produce a radiation pressure. So can we utilize the radiation pressure of thermal radiation to propel a nanostructure? To do so, I designed this nanostructure that consists of two different layers with different optical properties, and because of the different interaction of these layers with the surrounding thermal radiation, is going to get a new force will appear and it will get propelled. I modeled this nanostructure by means of a gray body, in which we have the Planck's distribution, and we have to take into account some of the different emissivities of both layers. As I said, the interaction with the thermal radiation bath will give rise to a force that depends on the difference of the reflectance of both sides. We need different optical properties in the two layers. Now, of course, we would like to have two layers that are as different as possible. So the ideal limit will be to have a black body and a perfect reflector. And in this way, we can actually give analytical expressions of these integrals that, in the case of the power radiated, is just the Stefan Boltzmann law, because one of the layers was a black body, and also we obtain a similar expression for the force. We plot it. We can see that we can actually have a force that is highly dependent on temperature, and something interesting is that we obtain a positive or a negative force depending on whether the nanostructure is hotter or colder than the environment. Now, what is really important is that actually, by considering realistic materials, we can use, for example, silver as a reflector and silicon carbide as an absorber or an emitter by reciprocity in the infrared. We can obtain results that are on the same order of magnitude as this ideal limited. We can also explore different configurations of nanostructures by changing the absorber layer with varying results depending on the material. Now there is a force in our nanostructure, but of course this force is not going to propel our nanostructure forever. This arises from the exchange of photons with the environment. So we are going to have that the structure is going to get accelerated as it thermalizes with environment. So let's study the joint dynamics of the temperature and the velocity. For the temperature, we just have to integrate the power radiated, and for the, and we can see here how the nanostructure thermalizes, starting from a temperature of 800 Kelvin to the temperature of the environment of 300 Kelvin. In the case of the velocity, we have to integrate the force acting on the nanostructure. And we can see that, as we suspected, the nanostructure accelerates as it thermalizes. But once thermalization is completed, it reaches a terminal velocity. And of course, this terminal velocity is going to depend a lot on the properties of the nanostructure, both the optical properties and on the inertial quantities, the heat capacity and the mass. It also depends on the initial conditions. So if we go to a lower initial temperature of 400 Kelvin, we can see that we obtain a smaller terminal velocity. And actually, by using our ideal system, we can explore this dependence of the velocity with the terminal velocity with the initial conditions, and see that it is linear on the difference of the initial temperature of the nanostructure and that of the environment. Now, I have told you that our nanostructure reaches a terminal velocity. So it will look like this nanostructure, once it is thermalized, will move at this speed forever. But this is not entirely true, because when our nanostructure moves with respect to a thermal radiation bath, new effects arise due to the Doppler shift that that it perceives from the thermal radiation photons. This is the concept behind thermal radiation drag. It's a concept that was introduced more than 20 years ago, in which, well, as I was saying, the Doppler shift perceived in the reference frame of the moving nanostructure, it perceives that the photons that are propagating against the movement are blue shifted, and the ones propagating with the movement are red shifted. And because of this imbalance, a new force, the drag force, will arise that opposes the movement. Now, what I find really interesting is that even if you go to outer space, you will still feel this force, at least up to some extent, because you will be subject to the microwave cosmic background that is around 3 Kelvin. So it's really cold. The force wouldn't be big, but it's still really interesting. And another notion that I find really interesting is that it looks like the photons are behaving as a viscous fluid that are preventing the motion of our nanostructure. So we are going to play a bit more with this idea. So we have the thermal radiation drag. As I said, it resembles the viscous drag that appears in fluid dynamics. And what I learned in my fluid dynamics course back to the undergrad is that when you give a more interesting shape to your object, new effects can arise. For example, in the case of an airfoil, you can design it to obtain a lateral force that acts as a lift force to sustain gravity. So the question here is, if we give a more interesting shape to our nanostructure, for example, this anisotropic shape, what happens? Will new forces arise? So this is the topic of this next section, where I explore the movement of an anisotropic nanostructure in a thermal radiation bath. And we are going to explore the joint dynamics arising from the anisotropy of the nanostructure and the anisotropy induced in the thermal radiation bath due to the Doppler shift. Now, I did this calculation by means of a dipole approximation in which the polarizability was modeled by means of a reciprocal response and an isotropic response, giving rise to this polarizability tensor. We are going to calculate the average over the fluctuations of the electromagnetic field by means of the fluctuation dissipation theorem that relates the average over fluctuations of the electromagnetic field with some dissipation function that in the case of the electromagnetic field, the electric field is just proportional to the density of photonic states. Of course, here the Bose-Einstein distribution is also involved, and in this case, because of the movement of the nanostructure, it's going to be Doppler shifted. This is really important, and is what is going to give us the effects that we are going to observe. With all of these ingredients, we can calculate the force, we can calculate the drag force that I talked to you before, but very importantly, a new component of the force arises. A lateral force, this y component of the force, that depends on the xy component of the polarizability, and in this way, it only appears if our nanostructure is anisotropic. Now, we are going to make some approximations to simplify these expressions. We are just going to make some simple assumptions. We are going to move at a velocity that is much smaller than the velocity of light. We are going to work at low frequencies. And by means of these simple assumptions, these reasonable assumptions, we derive closed form analytical expressions that include an explicit dependence on the orientation, on the angle. And the amplitude of this force is going to depend to this small f function that depends on, at the same time, on temperature, volume, the material properties through the conductivity, and also a geometrical factor accounting for anisotropy. So let's study the dependence of the force with orientation. If we plot the lateral force, we can see something interesting is that its sign depends on the orientation of the nanostructure. We can have positive and negative lateral forces. And we can see that it vanishes when the principal axes of the nanostructure are aligned with the trajectory. So we can see that the role of this force is to align the trajectory to the principal axis of the nanostructure. If we now plot the drag force, we can see that it is always larger than the lateral force, but we can optimize this ratio such that they have the same order of magnitude. And in particular, now I'm going to focus in this orientation where the angle is pi/4, because we see that the lateral force is optimized. Now we are going to study dependence with the aspect ratio, defined as the ratio between the two axes of this spheroid. And we are going to plot the results for some set of, for some choice of parameters. some choice of temperature and the conductivity, and something that we can observe is that the force decreases with conductivity but increases with the temperature. And the same occurs for the drag force. This can be understood by accounting that the thermal radiation force increases with the number of photons, high temperatures, and high absorption. Now, if we look at the aspect ratio, we can see that the ratio of the lateral force to the drag force is maximized when we have a prolet spheroid, which is approximately one-dimensional. We move to an oblate spheroid, this is a bit decreased, and of course the force just vanishes when we have an isotropic object, which is the case of a sphere. I have shown to you that the anisotropy of the nanostructure, together with the anisotropy of the thermal radiation bath, can induce a new force, this lateral force, but there is more. That has been actually been hiding here in my schematics for the whole time. There is a torque. So let's understand why this torque appears by means of a known example. This other paper that I showed to you before, in which we have first anisotropic object, which is a birefringent crystal, and we have a second anisotropic medium, which is this liquid crystal that can reorient with respect to the birefringent crystal. And because of these two anisotropic media, a Casimir torque will arise. Now, in our case, we actually have two anisotropic medium because we have an anisotropic field because of the Doppler shift, and of course the anisotropic character of our object because of its geometry. And these two systems are going to tend to align with respect to each other by means of this torque. I have shown to you that the thermal radiation drag can tend to stop a particle that is moving at a constant speed. But there is actually also a similar effect for rotating nanostructures. You can also have a Casimir friction, a Casimir torque, that tends to stop a rotating nanostructure. And what is also really interesting is that if we, instead of just one nanostructure, we have a whole chain of these nanostructures and make one of them rotate, this angular momentum will be transferred along the chain. And the way that we can understand these effects is by thinking that this rotation of the nanostructure is creating an imbalance on the absorption and emission of left and right-handed photons. And in this way, it's breaking this symmetry. This introduces the last section of my talk, in which I will talk to you about the joint transfer of energy and angular momentum between two nanostructures that in general can be at different temperatures, inducing a transfer of energy, and at different rotation speeds, inducing a transfer of angular momentum. And we are going to see how both of them are modified. So, to do so, we have to characterize the torque and the power transfer between the nanostructures and account for the effect of the fluctuating dipoles and the fluctuating fields. Unlike the previous cases in which we had an isolated nanostructure, here we have two nanostructures, and we have to study their coupling. We have a two-body problem in which both nanostructures are coupled. We have to take into account as well the effect of rotation in the polarizability model, and as we did before, we are going to use the fluctuation dissipation theorem to calculate the average over fluctuations. So, I'm going to skip all the derivation of the equations. I'm going to show you just the final result for the Casimir torque. I'm going to explain you what each symbol in this equation means. We have C, that it's a coupling constant, including the response of the nanostructures and also their separation. Theta is the thermal frequency. It's a quantity with units of frequency that is just proportional to temperature. So we will use it to characterize the temperature of each of the nanostructures. And then this capital omega is going to represent the rotation frequency of the nanostructures. Now, our two nanostructures are going to behave as a closed system in which the angular momentum is conserved. And we can see, just by looking at this expression, that the torque tends to synchronize the rotation of the nanostructures. We can see that it just vanishes when the rotation frequency of the two nanostructures are the same. Regarding the radiative heat transfer, as I said, we characterize it by the power transfer between the nanostructures. And in this case, we have a more complicated expression. So we also have that the energy is conserved, but I'm going to analyze this expression in more detail in the next slides. First, we can focus on this term here that looks a lot like the Stefan-Boltzmann equation, in which the dependence with temperature is quartic. recall that this is theta is just proportional to the temperature. And we are going to group the terms into two categories. The terms whose sign depends on the temperatures, and the terms whose sign depends on the rotation frequencies. And the interaction between these two different terms is going to give rise to really interesting behavior. I'm going to analyze a case in which the temperature of the first nanostructure, this red nanostructure, is hotter than this one here. Again, recall that this just measures temperature. And we are going to plot the power transfer between the nanostructures as a function of the rotation frequencies of both nanostructures. There's a lot to say in this plot, so I'm going to separate it into different regimes. First, we can have a regime in which the power transfer is increased, a second regime in which the power transfer is decreased, and what happens in this regime is that this term here, whose sign depends on the rotational frequencies, becomes negative and opposes the conventional transfer of energy. And when that term, this term here, it's not only negative, but becomes larger in magnitude, then we are going to have that the power transfer is reversed. In such case, the power transfer will be from the cold nanostructure to the hot one. So we can see that depending on the parameters of the system, we can have a lot of flexibility and a really rich behavior in the radiated heat transfer. I was really interested by this last case, so I'm going to study it in a bit more detail in the next slide by means of studying the energy, the different kinds of energy involved in the system. I'm going to study a more specific case in which, apart from the temperature of the first nanostructure, I also fix its rotation frequency, such that we are studying a cut of the previous plot, and I'm going to signal the regions in which the power transfer is positive by a quick green background, and where it's negative by a means of a purple background. As I promised, I'm going to study the different kinds of energy involved. First, the rate of change of rotational energy, the product of the torque to the rotation frequency, plotted for the two nanostructures. I also plot here, I'm also going to calculate the rate of change of internal energy. And just by looking at the plot, we can realize something interesting, which is that in the purple regions, the regions where we have this reversal of the heat transfer, we have that the difference in the rate of change of this rotational energy is larger than the difference in the rate of change of internal energy. And this is actually something that we can also find in our equation for the power transfer, because we can identify this term with the internal energies and this term with the rotational energies, giving rise to this analytical condition to observe this reversal of the heat flux. And in this way, confirming this kind of intuition that this reversal is rising from an imbalance in these different kinds of energy involved in our system. As a final note, very important, here this system is able to transfer energy from the cold nanostructure to the hot nanostructure, because to keep the particles rotating, we will need a continuous input of work so that the nanostructures don't synchronize the movement. So we are using an external input of work so that we can reverse the heat transfer in the same way as a refrigerator, for example, would do in more classical terms. Now, this finishes the results. I'm going to give some conclusions. We have studied lattice resonances in periodic arrays of metallic nanostructures. We have explored new configurations, and in particular, we have explored a new material, graphene, as a platform for achieving collective lattice resonances. We have explored new configurations of the unit cell to sustain excitation of lattice resonances, out-of-plane lattice resonances at normal incidence. And we have unveiled as well the role of the electric-magnetic interaction, which is many times neglected in systems of metallic nanostructures. And actually, they are really important in the case that you have collective modes, as we have seen. And finally, we have ascertained the role of the excitation source to excite these resonances. And also, we have bridged a gap that was missing between plane wave theoretical studies and experiments. In a different context, the context of phenomena induced by fluctuated electromagnetic fields, we have explored the interplay between thermal radiation and Casimir interactions to show the propulsion of structures with an asymmetrical optical response. We have predicted a lateral force and a torque in moving nanostructures that occurs if the nanostructure has an anisotropic profile. apart from the well-known drag force. And we have also explored how the heat transfer is modified in the interaction of two nanostructures because of the transfer of angular momentum between them. With this, I would like to thank the current members of my group, the past members of my group, the people that I have the pleasure to collaborate with during the thesis, and also the funding. In my case, I'm just using a model in which graphene is perfectly two-dimensional, and it doesn't depend on the thickness. It will depend on the thickness, on the sense that you could have a structure that actually is three-dimensional, that has an additional degree of freedom, and in that case, it will actually will matter. It will change with the thickness. Whether that model with a finite thickness is more accurate, I'm not sure about it. Probably yes, because I mean everything has at least some thickness, even if all the atoms in graphene lay in the same plane. But well, considering a different thickness is also considering a different shape, so both are related. So your question, maybe I'm not getting your question. Your question was whether it's more important the shape or. It is only the shape, only the geometry. And for example, even if you have something with a finite thickness, of course, if you increase the diameter but keep the same height, your values of eta and p will vary. But if you keep the same aspect ratio, then it will be exactly the same, because this value only depends on the geometry. So yes, I think at some point I compare it, and actually, if you compare this case here, these resonances are actually a bit broader than the individual resonances. So the interaction actually is giving you a broadening. Okay. Yes. Yes, it is something that it is not obvious until you make the calculation, I will say. But well, you could relate it to the fact that the response is large for let's say an array of ribbons with a magnetic field. The response is large in the x direction, at least in the way I define it, because it's where you obtain the localized surface plasmon. Then once you turn on the magnetic field, everything gets a bit more convoluted, and it's difficult to say beforehand, I will say, whether you will obtain a large response in the y direction. You can observe some feature of the lattice resonance induced by the magnetic field, and I kept it for completitude, let's say. But yeah, I don't think there is a really intuitive explanation as to why the response in the y direction, once you support the lattice resonance, is that small, other than, well, for an array of ribbons, you usually will expect this in the absence of a magnetic field. Other different geometries, what do you mean by that, sorry? For the cases that I explored, it behaved really similarly. Yes. This is something really important, and that maybe I forgot to mention in more detail. I was talking about this electric magnetic interaction that is the working principle of our out of plane resonance. And basically, we need to optimize this kind of interaction. Here I only show you the set Y component, and you can see that it contains its maximum values along this line, but also this line, but changing sign. And we have to take also into account, but I didn't show it here, that there are more components of this electric magnetic coupling. And in particular, apart from the set Y component that I was showing, you also have a set X. So you have to optimize this interaction at the same time for both components. And this happens, I think I show it here, for these 4 configurations. So it is crucial that the particles lie at those positions, relative positions, to sustain this mode. And by symmetry, these 4 configurations are equivalent, actually. Yes, this is something that the lattice resonance could be used for. First, you can think about adding a layer of some organic dye or something that you can strongly couple to your lattice resonance. And of course, if you add a layer, this is going to have a certain width, and you would like to have an excitation along the whole layer, let's say, not only in a tiny region like you will achieve with a localized surface plasmon. And also related to that, lattice resonances have been shown to be useful for coupling emitters that are in different that are relatively far away, because the lattice resonance can mediate this interaction. And well, this is also something that it's related to what we saw by studying the Gaussian beams. Because, well, yeah, you could see that the lattice resonance doesn't remain localized where you excite when you have your excitation source, but it's able to propagate along the array. Enhancing the emission of? Yes, they can be used to enhance certain excitations, certain transitions. Or what we thought is that something unusual about this is that the high magnetic field enhancement could be used to allow magnetic transitions, and this kind of interesting symmetry of the mode where they are anti-parallel, it will certainly be beneficial for certain for enabling certain transitions that couldn't be regularly excited. No, I haven't done any LDOS calculations. I have only done this far field excitation and looking at the near field response, but just by far field excitation. I will need to study it from a dipole in the near field. So your question is whether you have at the same time dielectric and just dielectric. Yes, it will work exactly the same. These results apply as well to the electric nanostructures, but the working principle will be similar. I mean, at the end of the day, you will need either an in-plane electric dipole exciting an out-of-plane magnetic dipole, or the other way around, an in-plane magnetic dipole exciting an out-of-plane electric dipole. And well, regarding this, it's also with metallic nanostructures, but we also studied the possibility of exciting an out-of-plane magnetic dipole, and this is possible even with the metallic nanostructures. But of course, it's not a large magnetic dipole because of the small magnetic polarizability of the metal. Okay. Yeah, it's always infinite. I mean, at the end of the day, everything is going to be finite and depend on some area. But the good thing is that we can normalize everything to the area, and then it just disappears when you calculate the acceleration and then the velocity. So it doesn't matter actually. And yes, answering the first part of the question, we are modeling always as an infinitely extended gray body. I see. So the axis of maximum polarizability is one of the principal axes of the nanostructures. Basically, for a prolate spheroid like the one that we see here, it will be the axis along which the nanostructure is longer, the long axis. Thank you. Yes, that is a really good point. As you said, in principle, in our calculations, the quality factor, if you get increasingly large lattice sum, can grow unbounded. However, this is in our model. This is in the theory where we have a perfectly periodic array that it's also infinite because it's periodic. However, if you go to a real system, the interaction is not going to be infinite. The first reason is because the system is actually finite, and this is going to limit how much interaction you are going to have between your nanostructures. This is similar actually to what I have shown for Gaussian beams. That, well, if you are only exciting a few particles, then those few particles maybe they cannot sustain the resonance. In the same way, you need an array that is large enough. Then it is not only the size, but also you have to have an array that is perfectly ordered. And any deviation from this perfectly ordered, whether it is because there is some uncertainty in the some error in the distance between the particles, or because actually they are not exactly equal particles, is also going to affect. Then there are other effects like, well, here for simplicity, these arrays are just laying in vacuum. But if you have a substrate and a substrate that are not index matched, this also can degrade your interaction and kill your resonance. So basically, there are a lot of experimental factors that will occur in a real array when you fabricate it that will limit your interaction and thus also your quality factor. Yeah, yes, that's another point. If you go to the limit where you mentioned where your resonance wavelength is super far away from the Rayleigh anomaly, you will have almost no nanostructure basically. But well, ideally you will still have a lattice resonance. In certain cases where we have seen for graphene that, for example, it has a steep dependence on the filling fraction, and if you make you choose a small filling fraction, your mode disappears from the spectrum basically. There are other systems that are able to maintain a larger response. For example, when we use nanospheres, the extinction efficiency doesn't depend that much on the filling fraction, and somehow the decrease in the response of the nanostructure can be compensated by the fact that you have a higher interaction, and then the peak extinction efficiency is roughly constant, at least to some point. If your nanostructure disappears, everything disappears. I mean, it depends on the material. It does depend. If you choose the same parameters but two different materials, the material that has the higher non-radiative losses is going to have a resonance with a lower quality factor. But you can always say, okay, but I go to larger periods until my quality factor is as large as I want. You're right that I could choose a different material, but in this case, what we are exploring is not really some different materials, but by just taking something that we know, for example, silver, and exploring new configurations like this bipartite array or the excitation with the Gaussian beams. Trying to change one thing at a time. More or less, yes. More or less, yes. Depending on where the polarizability crosses the lattice sum, it can be almost exactly the same as the individual response. We can have some cases where you actually can have a broadening, as I was explaining before to Angela. So yes, there are some cases where you see basically the raw individual response. Yes, you could say that by summing both of electric dipoles, it will be zero, but that doesn't mean that it doesn't have an effect. Both dipoles are creating a great response, a great absorbance. Yes, I think I see your point. Well, actually, at the end of the day, this is a resonance that we are exciting thanks to a magnetic dipole. And well, this kind of resonances, if you think, for example, in terms of mirror resonances, these are magnetic dipoles, right? And what electric and magnetic dipoles are, or more generally, electric and magnetic dipoles modes, sorry, are different in the case of mirror resonances is their parity, their symmetry. And one is even and the other is odd. And we are creating a mode that has the symmetry of the magnetic field. That's why we are able to excite it, even though our system has inversion symmetry. It's a bit how you want to see it. We like to see it this way because it's what allowed us to create this mode, because we came from the constituents and say, okay, if we want to have a mode with these properties from these particles, what shall we do? Yes. Yes, because the electric-magnetic interaction is dephased with respect to the electric-electric one. Well, yes, you could have it, for example, this. You can, for example, come with an angle, and then you will induce an out-of-plane electric dipole in a monopartite array, I'm saying. Or you could also create an array with nanostructures that have a more complicated shape. For example, that they have some XZ component of their polarizability, just the raw polarizability of the nanostructures. And in this way, you could excite it. This has been done, actually. Than the other. I think this case was the optimal one. It will still work. I think this kind of symmetric case was the optimal one. Yes, yes, we have actually done it in a work that didn't make it to my thesis. That was led by Luis Cerdan, that is here sitting. And it's basically you can structure a light beam such that it has out of plane components by using, for example, a radial polarization. In this case, the out of plane electric field component of the incident beam will be enough to excite this resonance. Yes, definitely. Yes, if they have a different optical response, yes, because ultimately the force depends on the different reflectance of both sides. So if they are patterned in a different way, certainly you will feel a force. But well, it's not a route that I think will be too promising because we have also we have already seen that by using some realistic materials without need of patterning, you already reach something that is super similar to the ideal case. So, well, it will work, but maybe not that much worth it. Yes, yes, that's it. Yes, that was something that we had to look to for materials that were not only having the properties that we wanted, but that had a tabulated permittivity in the literature that was extending in a spectral region large enough so that we could actually make the calculations. It turns out that these materials that I use for absorbers, they were measured with a huge spectral range. Sometimes I had to take permittivities from two works that were exploring different spectral regions, and then I was increasing the spectral region of my integral until I saw that it was converged. And then regarding the reflector, I always use silver, and to do that, we use a Drude model to extend it to low frequencies. Well, it depends on the temperature, but at the end of the day, around 10 microns was the important range. Well, one really big challenge is to modulate the materials to actually achieve that synthetic motion. But yes, I see it as a really promising route to verify these effects, which are sometimes these forces or torques are really small. And if you can have an analogous system to kind of simulate what these effects will look like, it will be really beneficial. Well, for me, this is a clear answer because it's one of my last projects. That is actually what is the it inspired the cover of my thesis, which is the project of the lateral force, because this came from an idea that I have, And while in the beginning of my PhD, I was following the ideas of my advisor and needed help from him to develop them. In this case, I had the idea. I discussed it with him. He guided me, but I took the lead in a bigger role, let's say. Thank you. Yes, that is one of the ideas behind this approximation. Well, basically, what it consists is that this green tensor that will include all the interaction within the nanostructure, we just keep at first the part that doesn't depend on frequency, which we identify with the quasi-static limit. And then we can, assuming that the distribution of the polarization density in our material is constant, which is an approximation, we can use the other fields that we have first neglected inside the green tensor to correct our polarizability, something like this. Well, it is divided by the area of the ion itself, basically. So you will obtain a sort of cross section by studying the extinction of one dipole, and then you normalize to the area of the unit cell. It's dimensionless. I mean, yeah, you have some polarizability. It's just that it is not resonant, let's say. But actually, let me find it. Okay, so yes, this component of the polarizability will be the Y component along the direction where it is uniform. And so you do have polarizability because, well, you do have a polarization density. It's just that it's not too large. It's not resonant. Could you repeat the figure, please? Okay. Well, maybe it is because the curve is too faint, but it's the gray curve. So it's the same that you see here, but there are more curves in the figure. There is some value, yes, there is. You have to choose the distribution that you want. We use the Gaussian distribution in reciprocal space because in principle it's something similar to a Gaussian distribution in real space, and laser beams are usually modeled as Gaussian beams. That's the reason, but we could as well consider other different distributions. I think that's there is, yes. Yes, I actually found that for certain parameters you can slightly excite an out-of-plane mode even with the Gaussian beam, because if you come with plane waves that are not normal incidents, this automatically imposes that you have some set component of your electric field. So the answer is yes, but yeah, it's not optimal for exciting the out-of-plane mode. You will need to move to a different polarization like this radial beam that we explore in different work. In which figure? Yeah, on figure 3.9. 3.9. Where you have to show you're dealing with the excitation area that you are able to excite, that is even outside of your inclination area, and it's not symmetric. That I guess that if you use something like a circular polarized beam, this is going to be symmetric. Yes, it's going to be symmetric because, well, it's degenerating in X and Y direction, so. You're asking about equation 4.1. 4.1. Okay, no, what I wanted to express is that since thermal equilibrium absorption and emission of photons have to be balanced, this imposes that the absorptivity and the emissivity have to be equal. And then one could model the emissivity in a reciprocal system by just the absorptivity. And then you can use that absorptivity in a case where the temperatures are not equal, because you already know that the emissivity and absorptivity as response functions are equal. Okay, I will answer in a moment. Okay, so in the case of the drug, in my calculations, it's always negative. Maybe this equation is not the most clear to see it, but no, what I have found is that the drug is negative, even if you look at every frequency independently. Yes, the off-diagonal components only appear if your principal axes are not aligned with the Cartesian axis. That's it. No, this is an approximation that we did throughout the whole work, in which we just keep terms that are proportional to polarizability. And basically, this means that dissipation through absorption is dominating, and we are neglecting some radiation through scattering. Well, depends on the system, I guess, on the material that you are using. If you are using a metal where this can be described as a good approximation, then no. If you go to something that doesn't absorb, then you will need to take it account, because that will be the whole interaction actually. Yes, I think you got it. Basically, if you have a force that is perpendicular to the velocity and you let your system evolve, this is just a centripetal force that is going to induce a curvature in your movement. And well, basically, this force will act until your trajectory is aligned with the principal axis, but it doesn't induce a reorientation of the object. This is done by the torque. So basically, I'm going to try to illustrate it with the pointer. If you start with your particle oriented in this way and it's moving in this direction, what it will do is that it will start moving until it's aligned, the trajectory is aligned with the long axis where it has the maximum polarizability, and then it will move in that direction until it stops because of the drag force. It's a super interesting proposal. Thank you for that. What it's really interesting. What I have thought is that, well, maybe you can, since you can transmit angular momentum through this change of particles, maybe you can build a chain that where the momentum is transferring to each of the particles, something like that. But this is a really nice suggestion. Thank you. Well, this is indeed an approximation because, as you pointed out, we are not exciting the resonance when we are at the pole, but somewhere in the real axis close to the pole. And the reason is that, well, we cannot excite something that it's in the, let's say, in the imaginary part of the complex plane, unless we consider something like a growing field or something like this. So restricting our analysis to CW prevents us from doing so, and we can only work close to the pole, but not actually in the pole. So, yeah, observing imposing a resonance condition only on the real part is indeed an approximation. So yes, for sure, it has to do with all the dissipation in the system, both with the non-radiative losses as well as with the radiative losses. And sorry, could you repeat the question? I will say it's true. Yes, yes. Well, basically, by working near to the pole and imposing this resonance condition, we've seen that we can model the resonance in a really accurate way. So yes, I will say so. The disks? Okay. Well, it doesn't play a role because we are not trying to excite, for example, out of plane modes. If we were to excite, we were interested in some charge oscillation in the set direction. That wouldn't be possible, of course. In that sense, this array of made of graphene nanostructures or microstructures it's different. But then the polarizability, actually, you can define a polarizability that has exactly the same units as a three-dimensional object. And because again, you still have a dipole with the very same units. So in that sense, it doesn't change, and you can apply a really similar analysis. To come in at normal incidence. Exactly. Oh yes, it will be possible, and then your conductivity will also have a dependence on the wave vector, and then it will basically make things a bit more convoluted, a bit more complicated. But as far as I know, if you come with far field radiation, the local response approximation in graphene is a pretty good approximation, and it shouldn't change too much. Well, it could be because that way you will have more in parallel, more have a larger well, you will have a parallel component of the wave vector, which you don't have normal incidence, and then you will be probing the structure of graphene. So maybe it could play a bigger role. What I mean is that, well, every excitation, every current in materials produces electromagnetic fields that we can separate in terms of the ring tensor in near field, mid field, and far field components. And the ones that in a macroscopic scale are relevant are the far field components, because are the ones that don't they are not evanescent in the sense that they don't decay exponentially. However, if you put objects pretty close together in the nanoscale distances, these fields can actually become important and couple the response between material nanostructures, and can be utilized for transferring energy or heat in this case between nanostructures. And this happens if we, of course, if we are looking at the heat transfer between nanostructures that are close, are pretty near to each other. But doesn't matter if we are just measuring what it radiates to the far field. Well, I will say that it depends on the excitations that are supported by those nanostructures. That are, of course, they are going to depend on what materials are they made of. And for example, if you have a metal, maybe that supports a surface propagating plasmon polariton, then how this mode decays with distance, the distribution of its near field basically is going to shape how it's going to interact with the other objects in its proximity. Yes, I will say so. You will need to have a material that it's able to emit at those frequencies, and another one that is able to absorb that energy at those very same frequencies. Yes, definitely. So the way that we model this rotation is by considering two different effects. On the one hand, we consider that it can make an say, intrinsic effect on the response of the polarizability. And the way that we include it is through the term that includes not radiative losses, by considering that the relative speed that the electrons the charges inside the materials should have is with respect to the rotation of the nanostructures. And very importantly, we also have some kind of rotational Doppler shift in which the response of the nanostructures is Doppler shifted. And this is something that connects a bit with the case of the particle moving at relative speed relative to the thermal radiation bath, in which we see that these effects arise from a Doppler shift. In this case, we have a different Doppler shift, but it's also responsible for these torques that we observe. I will agree with that. This is something that actually is not possible to see in the equation that I have shown, because to obtain analytical expressions, I'm working off resonance. So actually, we couldn't be able to see the effect of these resonances. But I agree that when the Doppler shift matches the difference between these resonances, we will obtain larger effects. Is it correct? It is because, as it happens for a refrigerator in a classical thermodynamical system, we need to put an input of work in the system, such that entropy always grows. And in this way, we can prevent the nanostructures to become at relative rest, which is what we do because of this torque that is acting on them. Yes, in my system, actually we have a relative speed between two systems, between the thermal radiation bath and the nanostructure, and that's why we can have this force. This force only appears if we have a finite temperature, and thus we have a thermal radiation bath, not just raw vacuum, which will also have its electromagnetic fluctuations, but couldn't create this force. And one way that one could see it is, again, talking about anisotropy, because the motion of this object will remain the same forever at constant speed if your system is perfectly homogeneous and isotropic, but this relative motion is introducing an asymmetry, an anisotropy that is creating the force. Well, the fact that we have a thermal radiation bath at finite temperature and the relative speed between the object and the thermal radiation bath. Well, it has to be the linear momentum, because we are losing linear momentum in terms of this force. Maybe the entropy? Yes, I think it's possible to say it like this. Like what is coming in your front, it looks like it's a higher temperature than what is behind you. What about the side? Well, it's coming at the side, so then, well, I think no. I think what is coming to the side is not shouldn't be affected. Uh, maybe I don't understand well the question. Well, the from the perspective of the moving object, the thermal radiation bath is indeed anisotropic, in the sense that well, the photons that are coming in one direction are different from the ones that are coming in from the back, for example. But you're saying a different, like a temperature gradient inside of the object. I see. As seen from outside. Um, Perhaps yes. I mean, if you look from the reference frame of the laboratory, in the same way as you have this anisotropy in the thermal radiation bath, maybe from the different reference frame, you could also have it. Okay, I think I see your point now. Yes, there's indeed a peculiarity, which is that these nanostructures are inside a fluid, and in particular an ionic fluid. And when I say that by tuning the properties of the environment, you could tune the equilibrium distances between these flakes and its resonances, it's because you can also play with the properties of the fluid and add higher or lower concentration of ions. And these ions are playing the important role of giving some kind of electrostatic repulsion that is compensating with this attractive Casimir force. Yes, so we many times use the extinction because it includes both the effect of absorption on reflectance, or in the case of individual nanostructures of scattering, and thus it gives kind of a general view of the interaction of the object. But well, in experiments, what is usually done is studying the reflectance and the transmittance. And then one can derive the absorption inside of your structure and the extinction from these quantities. Well, in our coupled dipole model, we couple the nanostructures, our electric dipoles, through the green tensor. And once you have a substrate, this green tensor will be modified because you will have a contribution from the reflection from the interface of your substrate and your substrate. And in this way, your calculations could change. There are some ways of including it in a simple way to derive a lattice sum in the case that you have a mismatch between the substrate and the substrate. And in this way, you can study effects, as I was mentioning before to Ramón, of how the lattice sum is also degraded in these cases and the resonances. And not here. Well, it's out of simplicity. If you include a different but uniform dielectric environment, then the resonances will just shift. And then if you have the mismatch, it's true that they are degraded. I have actually at some point made some calculations for the case of the out of plane and the out of plane lattice resonance. Seeing this was kind of a strange configuration, we wanted to check if it survives making a different kind of nanostructures like nanodiscs that are more simple to produce in experiments, and also introducing conventional substrates and superstrate, in this case silicon oxide and PMMA. And you could see that the resonance survived with really nice properties. And actually, very importantly, we've been collaborating with some experimentalists that have measured this mode. And we actually submitted the manuscript yesterday. Let me see if I can find it. So sad, I don't find it. Well, you will have to believe it. Sorry. Yes, definitely. We have used it with some collaborations with experimentalists, with some systems that were not that easy to model with this semi-analytical coupled dipole model approach. In particular, it was a system in which you had an array of holes, and then some material was deposited inside the holes, such that inside of the holes you had some kind of nanostructures, and at the same time you had a layer of high index dielectric on top. And well, at the end of the day, you can model everything as some higher order multiples and try to couple them. But at some point, it becomes more useful to just do a full wave simulation, and this is what we did in these cases, for example. Which slide, sorry? A page or a slide? Okay, I will try. So, well, the first thing is that the one that one will understand these plots is by realizing that we are plotting trying to point to the x-axis will represent the relative position of the particles in the x-axis, and here the relative position of the particles in the y-axis, in the y-axis. And you can understand these different terms, this EE, for example, as the electric field that is being created by the electric dipoles in the array. And the relevant components of this interaction, the ones that are diverging, as we saw in the Rayleigh anomalies, are the diagonal terms, the XX, YY, and ZZ. And since these are the diagonal components, they cannot mix polarization in different directions. However, the electric magnetic coupling, or the magnetic electric, that we can understand as the electric field that is being created in the different positions of the unit cell by the magnetic dipoles. In this case, we can actually have off-diagonal components, and in particular components that mix the Z component that we are interested in with the incident components of the electromagnetic field, which is in plane. It is a large magnetic field, but it's something that is attainable in experiments. There are I have tried. I have not managed to achieve something much better, like maybe the order of 5 Tesla, something like this. But yes, you need some pretty large magnetic fields, but at least attainable. One possible solution is what you mentioned for the reflector, building some kind of black mirror. But actually, silver works so well that I didn't try in the end. It provided a really nice reflectivity of 98% or something like this, even if the layer wasn't too thick. So I didn't try. In this work, or yes. So this is actually something that I did, and you can actually make a sphere with a anisotropic dielectric tensor, and at the end of the day, this will give you some anisotropic polarizability that, when oriented in the proper way. So again, the principal axis of your permittivity tensor are not aligned with the Cartesian axis or with the velocity. Then you will obtain off-diagonal components of the polarizability that will give raised both to the to forces and torques. I see. I didn't think about that, but yes, from my calculations, you could obtain forces and torques that were of the same order. So if the field is able to probe the anisotropic geometry of your nanostructure, it was also able to probe the anisotropic character of your permittivity. Well, I have a lot to think about, but yes, I have enjoyed the PhD, so it will be a nice thing to continue in doing science.